Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to start with doing a proof of this particular theorem that we've stopped at. So the theorem, just to briefly recall, the theorem states that we have matrix A and B, and they're both invertible n by n matrices. Okay, that n by n is not seen. It's not like next to me. N by n matrices, and C and D are not square matrices. We're not sure if they're invertible, but we know they're not square matrices, assuming that n is different from m. So we have the following properties that we're going to prove. We say that A inverse is invertible if we get the inverse of the inverse of A. That should bring us to our original matrix A. And then the product AB is invertible if we can apparently do this. So the inverse of the product AB is just inverse of B multiplied by inverse of A, which is an interesting thing. I haven't seen this one. And then if we have AC equals AD, so these are two matrix, and this is just equal to C equals D. And if AC is the zero vector, then C is a zero vector. No, zero matrix, not zero vector, zero matrix with n rows and m columns. So let's actually try to prove some of these, okay? So we're going to prove A and B, okay? C and D will just leave as an exercise, but I think that should be easy. Cool. So let's prove A and B. So proving A, we're going to prove A. Since we say that A inverse, so we say that A is invertible. And if it's invertible, we know that if we multiply the regular A with its inverse, it's just going to be an identity matrix to n, assuming that A is n by n. No, it is n by n. So its inverse is also a square matrix n by n. And multiplying those two gives us an I sub n. And this implies A is the inverse of this A to the power of -1. A way of writing that is A is just the inverse of the inverse of A. So that's how we prove A. Because we know that if we multiply the original by its inverse, it's just going to be the identity. So that's how we know A is invertible. And that implies that A is the inverse of the inverse of A. Does that make sense? That means if we take the inverse of A, inverse, that's just going to be A. So inverse of A is A. Okay, that is confusing, but I hope that made, I think that makes sense if we write it. If I say it, it doesn't make sense. At least for me. Now, for B, to prove this, we want to note. So B again goes the product. So this was an interesting one. AB is invertible if its inverse is the product of B inverse and A inverse. And ordering matters, right? So here we're going to note that this product AB multiplied by B inverse times A inverse. This is equal to A, B, B inverse. So here, I'm actually just doing one of the properties of a matrix where you can multiply the first, or here I'm multiplying B and B inverse first. And then I'm multiplying A inverse here. And this is the same thing as A, the inverse IN. Since B times the inverse is just going to be I sub n. And that is just going to be A sub 1, A to the negative 1. And that's just the identity. So we say that this AB and then B inverse A inverse is IN. And a way to write this is we can say B inverse A inverse is this guy inverse IN. And so that's just going to be B inverse A inverse is the product AB inverse. Okay, that is really cool, right? I wouldn't have seen that. So that's how that works. Now, here's an interesting thing that we've been wanting to ask for a while now. How exactly do we find the inverse of some matrix? So how do we find A inverse? So we now develop a method for computing A inverse. So let's start. Suppose A and B are n by n matrices. Okay? And we say that their product is just the identity. So actually, they're inverses of each other. Where, so we're just writing components A sub 1 all the way to A sub n. So these are column vectors. B is this guy. And I, so we can write I in a nice way as well. I sub n could be written as the E, which this is what we call it in linear algebra, right? The E sub 1 all the way to n. Okay. So later, we will set B to be A inverse, but for now, using B simplifies notation. Okay, so we're gonna do that later. For now, we're gonna keep B. So if AB is the identity, then taking multiplication one column at a time, so we're going to say taking multiplication one at a time. How is that gonna look like? Well, we're multiplying this A matrix by one of the vectors of B, which is just one of the E. And we keep going. 2 all the way to N. Right? That's what's happening. And thus B sub 1 is a solution to the linear system. So this linear system of AX equals B, or no, AX equals E, where X is the one that we need to find. We'll do X sub 1 in this case. Actually, we don't need to. It's fine. And then we say B sub 2 is the solution to the same linear system, AX equals E2. And we keep going, right? Now we could solve these systems one at a time by transforming to reduced echelon form from each of the augmented matrices, right? However, since we do the same row operations for each matrix, we can save ourselves some work by setting up one large augmented matrix. So that's what we're going to do. We're not going to solve all of these in one go. Okay. And so we're going to set up a large augmented matrix. And we're going to go through the row operations once to transform the left half from A to I. If this can be done, then the right half will be transformed from IN to B, which is just A inverse. So in other words, we want this idea. We're going to have this large augmented matrix, so that vertical line. A is the matrix that we have, and then in the other side is going to be another matrix that we have, which is the identity. And we're going to transform this. We kind of already have the tools for that. Linear transformation to IN, and then this B, which is just the A inverse. Okay, so let's do an example of how this works. In theory, it looks nice. Let's see a practical example. Let's see how this actually works. Okay, let's find the inverse of A. Now, there is a nice way to check this, which we already know. Uh-oh. Why do I keep opening up this app? It's weird. Okay. All right, so we have this inverse. So this matrix A sub 2 by 2. And so we set up the augmented matrix. So how's that going to look like? This A, then the vertical line IN. In this case, it's I2. This is the same thing as 1, 3, 2, 5. And then the identity. Like that. Okay? Now, how do we do row operations on these? Now we do Gaussian. It's the same thing. We're going to do Gaussian. And I'm not going to expect that I get the same answer, but let's see. So the goal is to somehow turn this into an identity, right? So how do we do it? 1, 2, 3, 5, 1, 0, 0, 1. There has to be a way to turn this into an identity. Let's see. So the first thing I would do is try to make this thing a 0. I would multiply row 1 by 2, subtract it to row 2, and we put that in row 2. So the idea is I'm going to first try to convert these to this augmented matrix to echelon form, and we'll see from there where this goes. Okay. And I subtract this 2 minus 2, 0. 6 minus 5 is 1. 2 minus 0 is 2. 0 minus 1 is -1. And I keep going from here. Okay? So the next thing I would do is, well, for one, I would reset this thing. 1, 3, 1, 0. And then I would try to make, oh, this one's nice. I would try to make this guy a 0. This 3. How do I do that? Well, for one, I could make row 2 to be 3. And then, or actually, I could make it negative. And then I add it to row 1, and then put that in row 1. So let me do that. How that's going to work is row 2 multiplied by -3. This one I think is just 3. And then this first row is going to change. So 3 minus 3 is 0. 0 plus 1 is 1. -6 plus 1 is -5. And 3 plus 0 is 3. And I have it. I can put this back. And there we go. This right here is the identity. And then this at the other side is the inverse of A. So that's one thing, right? We've done Gaussian elimination. So now we know what the inverse of this guy is going to be. So the inverse is this one. And to check, we multiply A with the inverse. And so we could do 1, 3, 2, 5. You multiply that to -5, 2, 3, -1. This thing is going to equal to what? 1, -5, 3, 2. It's going to equal to an identity matrix. There we have it. Done. That's the inverse. So for a given n by n matrix A, so a square matrix A, if A is invertible, then this procedure will find A inverse. If A is not invertible, then the RREF, reduced row echelon form of A with identity, will not have identity on the left side. So here's a quick note. So if A is invertible, procedure works. So this method works. If A is not invertible, the reduced row echelon form of this guy will not have IN on the left side. So this is one of those cases where reducing it to RREF using Gauss-Jordan elimination, this is useful for finding an inverse of a matrix. Okay, so now we've talked about one useful case where RREF is actually useful, not just echelon form. Okay, and we have some other examples here which are mostly just about finding inverses. So let's just go through them. Okay, let me, let's do example 3. So here we're gonna let t of x be ax. So this means that t is a linear transformation where A, so if we know what matrix A is, then we know what the linear transformation is, or at least the function of it. Because these are, the matrix tells us the coefficients of the function, the numerical coefficients. So A here is a square matrix 3 by 3. Now we're asked to find the inverse, if it exists. Okay? So what's the idea? We're going to say that this thing exists. First, we find out if it exists. This thing exists if and only if A inverse exists. So to find A inverse, set up this thing here. And this should lead us to this. Okay. So this is our idea. So we want to find A inverse. So same thing as before, right? We just put in the numbers. Now somehow we have to get an identity on the other side. So this is going to take a lot of row operations, which I'm not willing to go through. But the idea is it should give us this one. I would personally just do this in a computer just because I think it's long. Like, why would you want me to do this? I just think it's weird. There we go. So thus we have the t inverse, and we put some function in there. We put some input vector in there, which is equal to A inverse. And we also put something in there. Now this A matrix that we're finding is going to be A inverse. And we have this. A way to check if we multiply the original by this one and see if we get back the identity. And we will get back the identity. This next example is going to show us what happens when there's no inverse. So let's proceed to example 4. You want to find the inverse, if it exists, of this A matrix. 1, 1, -2, 2, 1, -3, -3, -1, and 4. Okay, how do we do that? So first of all, again, we set up the augmented matrix. So we're going to have this A with an I3. So this is going to be like this. Then we set up this one. Then we're going to do some row operations, and we're somehow going to end up with this one. After doing enough of it, and us getting annoyed after doing it, we're going to end up with this one. So we cannot get to the identity. I wish there was code to do this. Okay. So we're going to end up with this or something different, but we're not going to get to RREF. So this is not equivalent to an I of 3 and an inverse of A. So this is one of those cases where we just can't seem to find the identity because we already made this one a 0. Okay. And so we can stop there since the left half of the bottom row consists entirely of zeros. And there's just no way to use row operations to transform the left half of the augmented matrix to I3. And so A has no inverse. Okay, cool. Let's continue. Now, this next theorem highlights how invertibility is related to the solutions of linear systems. And so we're going to walk through that. So we have this theorem, 3.26. And here, we're going to let A be an n by n matrix. Then we say the following are equivalent. Let's look at that. We say that our first statement, A is invertible. Our next statement, AX equals B, has a unique solution for all B. And this is provided or given that this X is just the inverse multiplied by that B. And when we do the homogeneous system, this thing has only trivial solution. And so we say it's actually linearly independent. So a fun fact is we can connect this idea. So something that we've seen before, if this has a trivial solution, we know that the columns of A, column vectors of A, If we put that into a set, that set of column vectors of A is linearly independent. And if they are linearly independent, then we say it's invertible, right? There's also one way of relating it to that. Or if we say that if we convert it to echelon form, the matrix A, and we see a pivot every column, then they are linearly independent. That set of column vectors is linearly independent, and so that A is invertible. So really, it's just connecting ideas all together, okay? And of course, we have a proof, which makes sense, right? Let's do a proof. Of course, when we have a theorem, we have a proof. So we're saying that A is invertible if and only if this T, this linear transformation, if it's equal to this, then we know it's a linear transformation. And we say that this linear transformation is invertible. What else can we say about it? So we only know that they are, or this thing is true. It is a linear, invertible linear transformation. And we've discussed this if this T, is it an if and only if? Oh, it is an if and only if. This T is onto and 1 to 1. So it has to have a pivot every row for it to be onto, and it has to be 1 to 1. Okay, what else can we say? This implies, so based off of this explanation, this implies that the points made in A, the point in A and the point in B, where A is invertible and this linear system in a compact form has a unique solution for all B, then X is the inverse times B. This implies A and B are equivalent. Okay. Now, by setting this B to be 0, B implies C. If there is this unique solution, then we know it's the column vectors of A are linearly independent, if that makes sense. Because we don't have free variables. If we have free variables, then the column vectors of A, the set of the column vectors of A is going to be a dependent set of vectors. And so we're going to have free variables. But if we don't have free variables, we don't have infinite solutions. We have one exact solution, which is a unique solution. Then we know the set of column vectors of A is a linearly independent set. And so we know, based off of that, there's a pivot in every column. And there's also a pivot in every row. Right? Actually, no, wait. No, that doesn't connect to pivot every row. There has to have a pivot in every row if we convert this A matrix to echelon form. So there's a pivot every row, which tells us it's is onto an onto linear transformation. And if those are true, A is invertible. And of course, m is equal to n. So we have to have a square matrix to get an inverse. Because if we don't have a square matrix, that's not going to be an inverse. Okay, cool. Let's continue. So B implies C. So now we need to show that C implies A. Okay, so how do we do that? We want to show that if Ax equals B has only the trivial solution, then it's A. So there has to be a way to explain from that point C to A. How do we do that? Well, we start with saying what C is. C says if this homogeneous system, say B is 0, has only, there has to be a way to explain this. The trivial solution, T is 1 to 1 by another theorem. To connect this, T is 1 to 1. So actually, there is a way to explain this. T is 1 to 1 since if there's a trivial solution, the set of column vectors of A are linearly independent. And if they're linearly independent, then by that theorem, T is 1 to 1. And if T is 1 to 1, we'll continue. So since A is a square matrix n by n, could be any letter, honestly. By another theorem, T is onto. I'm not going to say what that theorem is, but basically the idea is if it's a square matrix, T is onto. Why? Let's check. Let's check what the theorem is. It says 3.9 from section 3.1. I forgot what that is. By that particular theorem, 3.9. Oh, the unifying theorem. Because these are all equivalent. Oh, C and D. Interesting. If T is onto, what does that mean? T is onto means that there's a pivot in every row. So if there's a pivot in every row, I actually don't know what that means. So what? So what if there's a pivot in every row? Ah, these dots are so hard to connect. Wait, where am I? I'm saying something like A is a square matrix. Oh, I think I know why. Say we have. Okay, let's do A, B, C. Okay, let's do it 2 by 2. Let's try this. But I can't seem to access my eraser. I can't even erase. Let's say we have this. This is our A. This thing's a 2 by 2. If it's a square matrix, this can be a pivot. This can be a pivot. What if it's not square? Say like A, B, C, D, E, F. This one is a 3 by 2, so this is not square. There could be a pivot here, there could be a pivot here. Oh, there's no pivot in the other row. So we need to have a pivot in the other row. Okay. So T is onto if there's a pivot in every row of that square matrix. So T is, we're just connecting here, the points that we made. So since we said that, okay, T is 1 to 1, and it's also onto. What does that mean? T is invertible. And since they're the same thing as that A, so we know A is invertible. And therefore, this C, that point that we made in C, implies the point that we made in A. And I guess just to finalize it, if A is invertible, we have the following. We have AX equals B, which is the same thing as the inverse of A, and AX is just the inverse of A. Oh no, whoops. Yeah, my bad. This is right. Then that B vector, which is just the X inverse. No, X is the inverse of A and B. Because this one turns out to just be the identity at N. And identity times its own vector is still that same vector. And so we get this idea. Okay. Cool. Let's do another example. Example 5. Okay, let's try this example. So we want to find a unique solution to linear system. So here we're given a linear system. X sub 1, 3x sub 2 is 4. Then we also have 2x sub 1 plus 5x sub 2, which is negative 3. And from here, okay, is there a unique solution? There can be, right? This is a 2 by 2. So immediately we have to see that this is a 2 by 2. We have two variables and two equations. And if you convert this to an augmented matrix, it's going to have 2 by 2. So we need to set A to be the matrix with the coefficients. And we need to set this x vector to be x sub 1, x sub 2. Okay. Oh, and what else can we say? This B is 4, negative 3. I almost forgot that. So actually, based off of the theorem in 3.26, this thing has a unique solution for all B. And so we just have to write out this idea. This x vector is the A inverse of this B. And so what that's going to look like is the oh, they solve for the inverse. Huh. Okay, here they solve for the inverse. But just to show what the theorem can do, Oh no, did not mean to do that. We're just copying what it looks like. Then it's equal to x. And in this case, we also have a solution for x, which is 29, 11. So this thing here is A inverse. This thing here is the B vector. This thing here is the x vector. Where x sub 1 is 29, x sub 2 is 11. So not too complicated. Okay, now here's going to be a fun part. A quick formula. For inverses. It's so bad that for every matrix, we have to reduce it to row echelon form, RREF. But there has to be an easier way. Okay? So there is, but specifically in a 2 by 2 matrix, not for more. So say we have A, which is a 2 by 2, A, B, C, D. There exists a quick formula. And it can be shown that A has an inverse exactly. So we say A has an inverse. Here's a quick way to find if A has an inverse. AD minus BC is not 0. If it isn't 0, we know there's an inverse. Okay? So inverse is the following. A negative 1, which is 1 over AD minus BC. Multiply this scalar. So this is a scalar multiplied by a vector. D minus B minus CA. Okay, that's the formula. And so instead of using the augmented matrix and row operations to verify the formula, we can check it. So to check if this formula works, well, the way to check it is we just multiply A by its inverse. And so we're going to have this guy here. And remember, we can multiply it in any order, right? They multiplied by A, B, C, D. And this should give me so I would multiply the two matrices first. So this would give me 1 over AD minus BC. If I multiply this thing, it's going to be AD minus BC. And here it's going to be a 0, 0. Then here's also AD minus BC. And if we just multiply all of that by the scalar, it's going to be 1, 1, 0, 0, which is I sub 2, which is an identity. So it must be that this formula is correct. Okay, that's a formula I would remember, or I would put in my notes. Because it does help to know quick formulas like that. Okay, let's do another example. Example 6. Let's find A inverse. Given that my A here is a 2 by 2. So remember, this quick formula only works if A is a 2 by 2. And it's also invertible. So from the quick formula, we're going to have, so A inverse is 1 over AD. So this is 2 times 5. Whoops. 2 times 5 minus B, 7 times 1, all over 5, -1, -7, 2. And this is just simply equal to 5/3, -1/3, -7/3, -2/3. Oh no, this is positive. And voila, there's my inverse. To check, we just multiply these two things together, see if we get the identity. And you can do that. And now, based off of all of that stuff, we can now update the unifying theorem that we've been using. So let's just update the unifying theorem. And this is, I think, version 3. So we've been adding a lot of stuff from this. So summarizing the results we have proved about invertible matrices, we're going to add one more important condition to the unifying theorem. Let's do it. So this unifying theorem states that, say we have S, and this is a set of vectors, A sub 1, all the way to A sub n. So this is a set of n vectors in Rn. I'm gonna shorten that, because I don't like writing English. I'm gonna say this set is a set of n vectors in n dimensions. And we're going to let A be an n by n. Oh, wait a minute. Didn't say that there, huh? We're going to say this A is a matrix containing these vectors A sub 1 to n. So again, we have A defining it as a column of vectors. And another thing we're going to let T from R n to n. So note here we have the same dimensions. So this T has an inverse linear transformation. So this thing is given by this T with some input vector x, which is just a mat vec of that matrix A to x. Then we say, then the following are equivalent. So here's what we know so far. So A, we know that this set spans Rn. What does it mean when it spans Rn? It's in that area of Rn. How do we know? There is a theorem, which I think I memorized now, is that if there's a pivot every row, say we convert these sets of vectors into a matrix that has columns of vectors, and then we do that as an augmented matrix, or just a matrix. We use Gaussian elimination, get the row echelon form, and check if there's a pivot every row. And the number of pivots that we get from counting each row is the n that we put in Rn. And that's what that spans. That's what that set of vectors span, Rn. So these are n pivots. Okay? B. So I'm just going to briefly go through them. It's just like a summary. We say S is linearly independent. Now, what does that mean? That means, given the set S, we cannot write one of them as a linear combination of the rest. Okay? What else does that mean? That means if we somehow make this into an A matrix, we have to check if there's a pivot every column. And the number of pivots that we count for each column is the number of vectors that are linear. If we put them in a set, they're linearly independent. Okay? What else can we say? Oh, AX equals B has a unique solution for all B. I'm going to write this in a mathy way. For all B in Rn. So based off of B, the point in B, and A, if we have a set of linearly independent vectors, A sub 1 to n, say that whole thing is linearly independent. We have n pivots when we count them per column. And so that means we're not going to have free variables. We're always going to have one exact solution. And so that's what that means. There's always going to be one exact solution for all B that we choose to have. Okay? What else? D is onto. T, I mean, not D. T is onto. That means there's a pivot every row. And so they span Rn, and they're also an onto linear transformation. Is 1 to 1. This immediately connects us to B, where the set is linearly independent, because there's a pivot every column. So T is 1 to 1. So all of these are really interconnected, which is a lot. And lastly, here's the nice one. A is invertible. Why? T is onto, and T is 1 to 1. And this is n to n. Linear transformation is from n to n. So we have a square matrix A. That's it. Okay, nice. Now, of course, there's going to be a proof for all of these. How do we connect all of them? Ay. We'll see. But all the 6 conditions are equivalent from A to F. Okay, I'm going to stop the video here. And the next thing I'm going to talk about, this is optional material. But I'm going to talk about it anyway because it's not optional in my course. But this is optional according to the textbook. This is partition matrices. So it's still connected to inverses. But I'm going to talk about it in the next video. So I'll see you guys there.